Hi, in today's video, I'll be going through what are relations on sets. In the previous three videos, we have already covered what are functions and what are the properties of functions, how you usually use them, and what you can expect from them. But now, we like to remember that functions have a specific property on the subset of the direct product, such that for all x, there exists a unique y such that the ordered pair lies in the graph, which is just a subset of x cross y. But now let's pull away the idea of this uniqueness and also pull away the idea that it must have all the x. And that's what we get. We get a relation. For example, if you want to take a relation of A cross A to B, it's just providing a subset of A cross B. And so if you're inside this subset, if you're the order pair inside this subset, let's say x comma y, we say x is related to y. And this is just a proposition, so it's either true or false, not both, not neither. And you can see, since it's a proposition, most of the proving later on will be using just logic to do. And so, this example above, where 1 is less than 2, 2 is less than 3, is actually the relation set on, it's just a relation where it represents the less than symbol on the set of 1, 2, 3, 4, 5. And so now you can see how our relations that we have learned in the past in our more basic math courses in school, such as the less than operation, the equality, they actually can be all written as sets. And this is what it means to always say that everything in mathematics is to do with sets. But sometimes sets, of course, looks very unintuitive, and so people develop such notations to simplify it. Because you don't want to know the relation, but you rather know how the relation operates. What does it mean for two elements to be related? And as I've said, now a relation on the same set A is just a subset of A cross A. And functions are just special relations with properties. But why we care more about functions and relations is because of the well-definedness of the outputs. This allows us to map, to say like what is the element that it maps to. If you just say it's a relation, then you can't really say 1 is related, 1 is mapped to 2, 1 is also mapped to 3 if they're related. And so you really care more about functions throughout mathematics, but of course special fields requires you to use relations as well. And so just need to take note of the differences and why I go through relations after functions. Now, because of the well-definedness of functions, we have injectivity, where you only get one-to-one outputs, or on surjectivity, where you get everything in the codomain as an output, has an input to the output. But with relations, because we don't have this well-definedness, all of A might not even be used. We have other type of properties we consider. These properties include reflexive. So a relation is reflexive if every element in A is related to itself. We also can say a relation is symmetric. It means if x and y are related, y is related to x as well. We can also say it's transitive. If there are 3 elements in A, x is related to y and y is related to z, we can say x is related to z. So these are the different properties that a relation can have. And we say that a relation is an equivalence relation if the relation has all 3 properties, meaning it is reflexive, symmetric, and transitive. Let's take a look at an example to better understand what a equivalence relation is. For example, we define a relation on the set of -1, 1, 2, 3, and 4. The equality relation is an equivalence relation. Because -1 is related to -1, 1 is related to 1, 2, 2, 3, 3, 4, 4. It's symmetric because you can flip this too. It's reflexive as well. And it's transitive because none of them are related to like some other element. So there's no transit needed basically. You can also verify that the following three are all equivalence relation by proving the following properties. And you can see how our diagram creates some sort of sameness within the group that they are related to. And then we can treat this group as one giant set. If you don't really understand what I've just said, feel free to repeat the video. But you can imagine that because they are related, they have like similar properties in a sense. So, example 1, 2, 3, and 4, they are all positive, and so that's what it means to have the same sign. So, they are all related in a sense that they have a similar properties of being the same sign. -1 is isolated as because it's the only negative number, but it can be considered as a separate group that is disjoint from the others. So this gives rise to the notion of equivalence classes. Equivalence class is just a subset containing all the elements that is related to A. So, and then you can just gather all these equivalence class together, and later we'll talk about that. So it can be a singleton because A can be related to A as itself. For example, the -1, they are all grouped together, grouped as itself only. But it can never be empty because R is an equivalence relation. And so we'll always know that the equivalence class will contain A itself. Like this is a singleton, like it will contain -1 itself, even if it's grouped as alone. So you know that none of the equivalence classes are empty, and you know that you can group the whole space into groups depending on the equivalence class. And so you can see these are the equivalence classes for each specific example. Practice more and look at more examples to familiarize yourself in the textbook. But we like to note that with this notion of equivalence class and how they are able to break up the whole set into different groups that are disjoint from each other, this gives rise to the notion known as a partition. And we'll go through partition after we prove certain facts about equivalence class. So we want to note that if two elements are related, then their equivalence classes are exactly the same. So basically, when you gather all the equivalence class together, you don't need to repeat A and B if they are related already, because they are the same. So to prove theorem 1 is shown in the textbook. I won't go through that again. But what I like to prove is theorem 2, where if they are no longer related, this part is a not an equality. But not an equality don't really tell us much about the equivalence class. And so we actually can prove further that their intersection is actually empty, meaning these equivalence class are disjoint. So we are able to change a relation into an equality or set theory operation. And so to prove 2, we first do one implication. We suppose that they are not related. We want to prove that they are empty, their intersection. So suppose not, meaning that exists a C that is in the element of the intersection. C must be an element of the equivalent class of A. C also is an element of the equivalence of B. So C is related to A and C is related to B. This means that A is related to B, which is the contradiction. And so the intersection is empty. Now you prove the reverse inclusion. We suppose that it is empty. We want to prove that it is not related. We do contradiction again. Suppose A is related to B, that means A is inside the equivalent class of B because the equivalence class collects all elements related to B. But then A must also be an element of A, and so A is an element of the intersection, and so but the intersection is empty. This leads to a contradiction, and hence A is no longer related to B. You can see how the disjoint fact comes in and how this equality helps us prove things about relations, and we must be able to switch between the two when the context arises. Now, let's talk about the partition that I said earlier. A partition is the very intuitive thing in English where you imagine you have objects and you want to just partition them to, so it's like kind of a separation, as you like to say. So a partition of a set is to have non-empty subsets of A, so each of these pieces must be non-empty. But when you union all of them, you get the full piece A, or the full piece X, if you will. And then the intersection is empty, meaning they don't overlap. These two pieces do not overlap. For example, if you have like marbles, you can break them into two, but the same marble cannot be in both pieces. So that's an example to show what is a partition. But you can then say a partition also gives rise to an equivalence class. For example, an easy example would be to remember the remainder modulo class. So we'll talk more about this in number theory, but if you just remember that if you divide by 3, the only possible remainders are 0, 1 and 2, and so you can form equivalence classes on them to partition the whole set of integers into just 0, 1s and 2s. So this is what example 11.16 is saying. So we can write them as just 3 elements. So this set is also known as the quotient set. It's not really important the name, but it's just good to know that you can gather all these equivalence classes and form a set known as the quotient set. And this equivalence relation on the modulo 3 gives rise to this partition. And so an equivalence class forms a partition on a set. And the converse is true as well. Given a partition, we can form a relation by relating two elements if and only if they lie in the same partition set. So example, A and B lies in this, so we can just say A is related to B. The proof of this just follows from set theory logic, and so it's not, you can just prove it yourself, but I'd like you to remember how we thought of it and how it is quite intuitive how it arises. If you have any questions on this, feel free to leave them in the comments down below. I hope I've tried to simplify equivalence relations for you to better understand them. Thank you for listening and have a great day.